Alright, now so let's take a look for the example of LMTD, how to calculate for LMTD and how LMTD is being used when you are presented with problem statement. Okay, for example, a liquid food which has specific heat of 4 kilojoule per kilogram degree Celsius flows in the inner pipe of a double pipe heat exchanger. The liquid food enters the heat exchanger at 20 degrees Celsius and exit at 60 degrees Celsius. Alright, so this particular information is meant for liquid food. Okay, then the flow rate of liquid food is 0.5 kilogram per second. So this is the flow rate. This particular flow rate will relate to how we are going to calculate for the for the flow rate of the hot water later. Alright, in the annular section, hot water enters the heat exchanger at 90 degrees Celsius and it flows countercurrently. Alright, so this is your key point here. It flows countercurrently. Okay, this is the key point whereby when you are presented with this kind of problem statement, this will be the key point that highlighted to you that this particular problem statement is using calculation for LMTD. Okay, so the hot water, okay, this one is hot water, it flows at 1 kilogram per second. Okay, the flow rate is 1 kilogram per second. The average specific heat of water is 4.18 kilojoule per kilogram degree Celsius and assume steady state condition. Alright, so you are being instructed to calculate 3 items here. So whenever you are going to be calculating these 3 items, basically these 3 items are the step by step for you in order for you to get the final question, the final answer for the last question. Okay, this is this particular question is to guide you to get the final answer for this one, overall heat transfer coefficient. Okay, so the first one, calculate the exit temperature of water. Okay, exit temperature, if you notice, we have temperature inlet and outlet. This one is for liquid food. But then for hot water, it only presented with the heat, the temperature entering into the system at 90 degrees Celsius, but there is no T exit for hot water. Okay. The second one, calculate log mean temperature difference, LMTD. Okay, because when you calculate for exit temperature of water, then you will see that we have 4 temperatures. Okay, 2 temperatures for the liquid food and 2 temperatures for hot water. So when you have 4 temperatures, you cannot simply by calculating temperature difference. You need to calculate LMTD. Alright, and then the third one, if the area of the heat surface of this exchanger found to be 60 meters square, what is the overall heat transfer coefficient? So after you have calculated exit temperature, then you are able to calculate for LMTD. Then after that, this particular LMTD you are going to use to calculate overall heat transfer coefficient. Okay, so basically this particular question will give you around 10 marks in order for you to solve and get the correct answer. Alright, so how we are going to solve this problem? Please look at the next slide. Okay. For this particular problem statement, you need to use for a simple heat balance, whereby the quantity of heat in liquid food per second is equivalent to quantity of heat in hot water per second. Okay, because what happened here is that the Q from hot water is going to be transferred to liquid food. Alright, so the quantity from hot water, the quantity of heat from hot water should be equivalent to the quantity that is being received by liquid food, so that at one point they will achieve equilibrium. So that's why quantity of heat, Q of heat, is equivalent to Q heat of liquid food is equivalent to Q heat of hot water. Alright, so in order for us to solve this problem, you need to use the equation Q equals to mCp delta T. Alright, use the equation Q equals to mCp delta T. But since we have one part on your left hand side, this one is meant for liquid food, and then on your right hand side, this one is meant for hot water. So it is being denoted as mCpC delta TC. This one is meant for cold food, okay, because this one it serves as the colder part, okay. And then for MHCpH delta TH, this one is meant for hot water. Okay, the denotation of H, this one is meant for hot water. Alright, so MC, this one has been given as, this one is the mass flow rate. Mass flow rate for the liquid food that has been given in the problem statement. It is 0.5 kilogram per second. Okay, times by the Cp has been given as well for the liquid food is 4 kilojoule per kilogram degree Celsius. And then for delta T, it has been given that the exit temperature of liquid food is 60 degrees Celsius and the T inlet for liquid food is at 20 degrees Celsius. So we have 60 minus by 20 degrees Celsius. Alright, so this part is meant for liquid food. Okay, and then on your right hand side, this one is for you to calculate for the hot water. Alright, so the mass flow rate for hot water is 1 kg per second. This one again is mass flow rate for hot water. And then the Cp for hot water is 4.18 kilojoule per kilogram degree Celsius. And delta T for the hot water, we only have the T inlet. T inlet for hot water minus by T exit for hot water. Okay, why on your left hand side, why the temperature of liquid food is T exit minus by T inlet, whereby on your right hand side, the temperature difference, in order for you to calculate for temperature difference, it is T inlet minus by T exit, okay, T outlet. Okay, why is that so? Because the heat, alright, the heat from hot water, okay, temperature for hot water is higher compared to liquid food. And this particular process, in this particular problem statement, requiring to heat the liquid food, okay, at certain temperature. We want to achieve the liquid food temperature at 60 degrees Celsius. Okay, so again, it has been explained to you that when you want to calculate for temperature difference, basically it always from the higher temperature minus by lower temperature. So when liquid food, it enters the system, it enters at lower temperature. But when it exits, because this problem statement, it involves with heating, when it exits at 60 degrees Celsius. So the temperature is higher. So when you want to calculate for delta T of liquid food, so it is from the higher temperature to lower temperature. But then for hot water, heat from hot water is being transferred to liquid food. So we can expect that after the heat from hot water is being transferred to liquid food to increase the temperature of liquid food. So what happened to the exit temperature? The temperature of hot water will be reduced when it goes out from the system. Alright, so that's why from the calculation of delta T, it should be from higher temperature to lower temperature. So from the T inlet of hot water, whereby the temperature is higher, will be minus with T exit of hot water, whereby the temperature of T exit will be lower compared to T inlet. Okay, I hope you get it. Alright, so calculate this part. On your left hand side, calculate what is this particular value. And then on your right hand side, please make sure that you have this one unknown. Okay, and you need to calculate this unknown. Alright, So it is a very simple whereby you need to calculate all of this, but you need to leave this unknown and you need to get this particular value of unknown. Okay, the value of T exit for hot water is 70.9 degrees Celsius. Alright, so you solve the problem statement for number 1. Now we move on to the problem statement for number 2, whereby you need to calculate for LMTD and you need to use this particular temperature, okay, for T exit of hot temperature. So we have 4 temperature now. We have 60 degrees Celsius, 20 degrees Celsius, then we have 90 degrees Celsius, then number 4 is 70.9 degrees Celsius. So we have 4 sets of temperature. So you need to use LMTD, alright, in order for you to calculate for temperature difference. So again, for temperature difference, I have explained to you before of how to memorize the equation without you memorizing it. Okay, remember the diagram whereby this particular flow is counter current, it is not co-current. So you need to know how to draw and the direction of the liquid food and the hot water. Alright, so for example, this one is for liquid food entering. Okay, so this one is TCI, okay, and then it leaves. So this one is TC out. Okay, since it flows counter current, so the direction will be in opposite direction. So TC outlet, the one that joins in at the same on your right hand side, this one will be TH inlet. Okay, and then when it exit on your left hand side, this one is TH outlet. Okay, so how are you going to derive the equation is by you need to separate between section A and section B. This one is A, this one is B. So to ease your memorization of how to calculate the LMTD is very simple, whereby when you want to calculate LMTD, it is always with A minus by B, okay, and then divide by ln A per B. Okay, this one is the section. Alright, so what happened here is A is TH naught minus by TCI. Okay, this one is for section A, minus by B, for B is TC naught. This one is supposed to be THI minus by TC naught. Okay, divide by ln. Again, you take back this one, this particular A, TH naught minus by TCI, right, divide by THI minus by TC naught. Okay, so this will ease you how to use this particular equation. When you have this diagram and you can memorize, okay, which section belongs to which section, which temperature belongs to which part. Alright, so then you can calculate the LMTD by using the equation given to you, and you need to memorize this particular equation. But how to memorize is by simply using this particular diagram, and you are able to derive the equation on your own. And make sure that when you derive, you have the correct equation and the correct temperature, which one should be minus by which one. Okay, so this particular TE of 70.9, this one belongs to the T exit. Okay, T exit for the hot water. Alright, so plug in all the values that we have calculated just now, and then you should be able to get the value of LMTD at 39.5 degrees Celsius. And this particular temperature will be used when you want to calculate for Q equals to UA LMTD. Alright, so for the third part, you need to calculate for the U. You are not required to calculate for Q. Okay, but then Q is equals to, okay, Q equal to UA LMTD. Okay, delta T LM. Alright, so how are you going to calculate Q when you do not know what is the value for Q and at the same time you need to calculate for the U? Okay, you can calculate the value for Q from the equation over here. At the top part over here for the liquid food, okay, for the liquid food, you have the whole values for each parameter. You have the value for liquid food for M. You have the value for CP of liquid food. You have the value for delta T of liquid food. Okay, you can use Q for liquid food to calculate the value for Q here, or you can use the value for Q of H2O when you want to calculate for this particular Q. Because both of these particular Qs, you have known all the parameter, the M, the CP, the delta T. Okay, the M, the CP as well as the delta T. This one is MCP and delta T. So you can use either for the hot water or for the liquid food. In this case, for the third one, what I calculated is I am using the value from the liquid food. Okay, why I select for liquid food? Because the values has been given from the problem statement. Alright, for example, if let's say I use the temperature of exit temperature of hot water, but then when I calculate it wrongly and I put it here, then I will get the wrong value of U, or the value of Q is wrong as well. But doesn't matter, because when you calculate for the TE wrongly, then you will get the wrong value of LMTD as well. But at least when you use the Q for liquid food, the parameter that has been given in the problem statement, you can't go wrong when you want to calculate for the Q. Okay, that is my tips. Alright. Okay, and then just use all the values that is being given from the problem statement in order for you to calculate the value for Q. Okay, this one is Q, and then the unknown that we need to calculate is the U. The area has been given in the problem statement is 60 meters square, and then the LMTD, you have calculated this one as 39.5 degrees Celsius from the calculation of LMTD. So when you want to calculate for the U, then the value is 0.0338 kilojoule per second meter square degree Celsius. Alright, so you need to know where does this unit coming from. Alright, how this particular unit coming from. Okay, do not simply just putting the unit. When you have a wrong unit, then your answer will be wrong as well, because this particular unit, it represent for the unknown of U. Okay, so this particular problem statement and how you solve the problem, this one will gives you around 10 marks. Okay, for the overall calculation, starting from the first part, from the calculation of T exit. Okay, and then you need to calculate for the LMTD, and then you need to calculate for U. So this particular problem statement, it will give you around 10 marks. Now we move on for another example which is similar but then a different sample and different values. Alright, in a counter flow heat exchanger. So this is your key point here, counter flow. It is not co-current, it's counter current. In counter flow heat exchanger, water is being chilled by a sodium chloride brine. If the rate of flow of the brine is 1.8 kg per second and that of the water is 1.05 kg per second, estimate the temperature to which the water is being cooled if the brine enters at -8 degrees Celsius and leaves at 10 degrees Celsius. and if the water enters the exchanger at 32 degrees Celsius. Alright, so this particular problem statement is quite tricky for the students because it involves with the use of the words. Okay, comparing to the previous example whereby it's very straightforward, but for this one, you need to know what you are going to do, what you need to do. And then what are the values that has been given from the problem statement. Okay, so what you need to do is, alright, you need to make sure that you know what are the values that is being given to you in the first place. Okay, so the first one, this one is rate of flow for brine. Okay, brine is salt water, right? So I can simply just list out, for example, a brine is 1.8 kilogram per second. Alright, and then I have M for water is 1.05 kilogram per second. Alright, and then the question asks you, estimate the temperature to which the water is being cooled. Alright, so now this particular process, it involves to cooling water. To cool the water by using brine. Alright, so what you need to calculate is you need to calculate the temperature of water after it has been cooled. So what happened here? Brine enters at negative 8 degrees Celsius. Alright, so I have the temperature for brine. T brine in is negative 8 degrees Celsius. Then I have T brine out is 10 degrees Celsius. Can you see that this particular temperature, there is involvement of temperature increase from negative 8 below 0 degrees Celsius, okay? Negative 8 degrees Celsius, it increased to 10 degrees Celsius. Alright, so where does this particular heat is being transferred? This particular heat is being transferred to the water. Alright, so the water enters the heat exchanger at 32 degrees Celsius. So TWI, T water inlet, this one is 32 degrees Celsius. Okay, you need to know how to list out the information that is been given to you. Although the problem statement is quite tricky for you to understand which part is which part, but then when you list out, you will become clearer. Okay, so now what involved in this particular problem statement is that water is being chilled. Water needs to be cooled down. So the T water out is the one that is unknown. Okay, it is unknown because what will be the temperature of water going out after it has been cooled by using the brine? Okay, so if the area, so now the first part is you need to calculate for the exit temperature of the water. Alright, and then if the area of heat transfer surface of this exchanger is found to be 55 meters square, what is the overall heat transfer coefficient? Then you need to calculate for the U. Alright, take the specific heat to be 3.38 and 4.18 kilojoule per kilogram degree Celsius for the brine and water respectively. Okay, so this particular area, it is been given, area is 55 meters square, and you need to calculate, you and I, we need to calculate for the value of U. Okay, so when you have this particular problem statement, when this particular highlight, counter flow heat exchanger, so basically you need to know how to calculate for LMTD. Because when you want to calculate for U, you need to use the equation Q equals to UA delta T. But in this case, since we have 4 sets of temperature, 1, 2, 3 and 4 temperature, then this particular delta T, you need to use the LMTD. You cannot simply by using delta T that is need to calculate for 2 temperatures. For LMTD, you are dealing with 4 temperatures. Okay, so again the same problem statement, similar, almost similar, and how you are going to calculate for this particular U is whereby you need to calculate step by step from the exit temperature. Okay, 1 from exit temperature, and then 2 you need to calculate for LMTD, and for the third one you need to calculate for the U. Alright, it is the same step. So now let's take a look for the slide for to solve the problem statement. So again, you need to use the heat balance whereby Q equals to mCp delta T. Okay. Why this one is delta T? Because we have one side is for brine and the other side is for water. And each brine and water, they should have 2 sets of temperature, not 4. LMTD is 4 temperatures. Okay, so on your left hand side is quantity of heat in brine per second, and then on your right hand side is quantity of heat in water per second. So equalize both by using the equation Q equals to mCp delta T. On your left hand side, that one is for brine, and on your right hand side, that one is meant for hot water. Okay, plug in all the values that has been given to you and you have listed just now, as I have shown you how you should properly list all the values. It is important for you to list out all the values that has been given to you from the problem statement. You need to extract whatever the information that is been given to you so that it will be easier for you to plug in the values according to the parameter. Okay, for the M of brine is 1.8, then the Cp for brine is 3.38, and then delta T for brine is from 10 to minus 8. 10 minus by negative 8 degrees Celsius. Right? It is not the other way around. It is not negative 8 minus by 10. This one is wrong. It's supposed to be from higher temperature, whereby 10 degrees Celsius is higher compared to negative 8 degrees Celsius. Right? This one is delta T for the brine. And for your right hand side, on your right hand side, this one will be the M for the water. It is a 1.05 times by 4.18. This one has been given to you in the problem statement. Times by 32 is the temperature of water entering into the system, and then you need to calculate for the T exit. Okay, now what you need to calculate is T exit for water. Right, so use all the values. Okay, calculate. So when you calculate on your left hand side, you will get 24.95. That one is meant for the brine. And then for your hot water, this one is 32 minus by T. Then you should be able to get the value. Oh, sorry, this one after we have equalized all the values, then it leaves only 32 minus by T on your right hand side. Okay, so the T value is 7 degrees Celsius. TE for the water is 7 degrees Celsius. Okay, then you need to calculate for the LMTD, since this one is again for the flow of the liquid is by using counter current. Okay, the same thing goes. Just draw the diagram, a simple diagram, so that you are able to know which temperature belongs to which part. Alright, so it's totally up to you. Okay, for example, this one is TC naught, this one is TC exit, this one is TH. Sorry, this one's supposed to be TCI. Look at the arrow. See, I'm making the mistake as well, and you need to know that the representation of the temperature is correct. Okay, and then this one is TC naught, and then this one is THI minus by TH naught. Okay, which temperature belongs to which temperature? Okay, so use your the one that I have shown you just now. Okay, belongs to section A, this one belongs to section B, and then from there you can calculate for the LMTD. Okay, by using the equation of LMTD. So the LMTD is 18.3 degrees Celsius. That is the LMTD. And this particular LMTD will be used in order for you to calculate for the value of U. Alright, so Q equals to UA LMTD. And this particular Q, from this particular problem statement, it takes the values from the brine. Okay, you can use for the water as well, but then this one is for the brine. And UA delta T LMTD. Alright, so just plug in again. This one is MCP delta T. Right, this one is the delta T for the brine. Okay, and then on your right hand side, this one is UA delta T. So U, you need to calculate. This one is the unknown. A has been given. And LMTD is what you have calculated just now. It's over here, should be plugged in here. So the value for U is 0.11 kilojoule per second meter square degree Celsius. Alright, so this is another example of the use of LMTD and how to calculate the value of U when you are being given with 4 sets of temperature. Okay.